Welcome, everyone. Today we're diving into a brand new explainer that unpacks some truly dense, highly theoretical findings by Bioli, Gould, Ross, and Siskakis. We're looking at the real variable Cesaro operator. If you're the kind of person who loves seeing how abstract mathematical structures behave and sometimes totally rewrite their own rules when you change their boundaries, well, you're definitely in the right place. We're going to construct a detailed narrative retelling of the Cesaro operator on the L-squared 0,1 space and figure out exactly how it ticks.
To really grasp the gravity of this new paper, we got to start with its mathematical pedigree. Back in 1965, the classical Cesaro operator was heavily studied on the Hardy space. It was acting on analytic functions inside the open unit disk of the complex plane. It was this incredibly well-behaved, bounded linear operator that basically gave mathematicians a rich, complex playground to explore for a whole generation. But that brings us to the absolutely crucial question for our journey today. What happens when we move from that complex disk to a simple real interval? You see, transitioning from winding paths in the complex disk down to a strict real interval, specifically the Lebesgue space from 0 to 1, fundamentally changes everything about the operator's properties. By stripping away the complex plane, we're literally removing an entire dimension of mathematical freedom. The whole environment shifts, which forces the mathematical anatomy of this operator to transform in some really surprising and frankly super strict new ways. Here's our roadmap for this explainer. First, the classical versus the real operator. Second, boundedness, adjoint, and norm. Third, spectrum and operator normality. Fourth, visualizing the spectral representation. And finally, semigroups and invariant subspaces. This structure is going to keep us on track so we don't get lost in the equations.
All right, Section 1, the classical versus real operator. Let's anchor our understanding by using that classical operator as a baseline. Take a look at this fundamental divergence. Notice how the classical formula integrates along a path in the complex disk to evaluate analytic functions. Meanwhile, our new real operator integrates strictly along the real interval from 0 to x. It might look like a subtle tweak to the formula, but it totally removes the freedom of the complex plane. We're locked onto a one-dimensional track now. The math just isn't allowed to wander through complex space anymore. It's bound to the harsh reality of a single straight line. Moving right into Section 2, boundedness, adjoint, and norm. Our first real trial here is proving the foundational boundaries of this newly defined operator. So how do we tame infinity? When you're dealing with infinite spaces, you absolutely have to prove your operator isn't just going to spiral out of control. The authors brilliantly break down this proof of boundedness using Schur's test. If you're not familiar, Schur's test is this classic, incredibly powerful tool designed specifically for bounding integral operators. They carefully define an integral kernel and set specific measurable parameters, p and q. By calculating the integrals of these parameters against the kernel, they nail down the constant bounds, alpha and beta, both coming out to exactly 2. This perfectly maps out the operator's limits and proves, for sure, that it's safely and permanently bounded. And by mapping those integral kernels, we also stumble upon the exact formula for the adjoint operator. You can think of the adjoint as the operator's mathematical shadow, or its mirror image. Notice how the limits of integration flip here? We're integrating from x to 1 now, instead of 0 to x. Hold on to that thought, because this mirror image is the crucial key we're going to need to unlock the operator's most elegant properties a bit later. Because of that flawless Schur's test calculation, we get this beautiful moment of mathematical clarity. The operator norm of the Cesaro operator on the L201 Lebesgue space is exactly 2. There's no messy decimal, no abstract concept, just a crisp, clean integer boundary that firmly boxes the operator in.
Let's move on to Section 3, Spectrum and Operator Normality. Now that we have the norm locked down, let's explore its hidden traits.
To really peer into the spectrum, the paper uses a series of isomorphic transformations. Think of them as mathematical lenses. First, they stretch our interval from 0 to 1 all the way across the entire real line, from negative to positive infinity. Then, they push it through a Fourier transform. And this elegant sequence reveals something mind-blowing. Our complex integral operator is actually unitarily equivalent to a multiplication operator. In the math world, that is a massive win. Multiplication operators are just vastly easier to analyze. They literally turn tangled calculus problems into straightforward algebraic multiplication.
Now, look at the stark geometric contrast we're left with here. In that classical 1965 paper, the spectrum of the operator was a solid disk in the complex plane. But moving to the real interval acts kind of like a computational shrink ray. The spectrum completely collapses from a filled solid disk down to just its boundary edge, essentially a hollow ring. All that interior complexity just vanishes, leaving us with a perfectly crisp, one-dimensional perimeter.
And here is where the real operator truly outshines its classical ancestor. The classical version on the complex disk is just subnormal or hyponormal, but our real variable operator, it's strictly normal. That means it commutes perfectly with its adjoint. In plain English, applying the operator and then its shadow is exactly the same as applying the shadow and then the operator. Finding an operator that commutes this cleanly is a fantastic upgrade in how the math behaves.
Section 4. Visualizing spectral representation. Let's dive right into the spectral theorem and actually visualize what this mathematical entity looks like. Because our operator is both normal and cyclic, the spectral theorem guarantees we can represent it visually using a specific measure. To actually find it and give a visual shape to the operator, we use a constant function, just a flat line of 1 across our interval, as a geometric seed.
By taking that cyclic vector seed and pushing it right through our Fourier transform lens, we generate this exact bell-shaped measure. What you're looking at is the graph mapped out perfectly on the infinite real line. It traces the intermediate measure of our operator's influence, finally giving us a tangible, symmetrical shape to work with.
And this brilliantly illustrates the climax of the spectral representation. We take that beautiful bell curve we just generated on the infinite real line, and we seamlessly wrap it around the circular boundary of the complex disk. This creates our final measure, mu. It's the definitive geometric proof of the operator's unitary equivalence to a clean multiplication operator, perfectly distributed right on that circular curve.
Finally, Section 5, Semigroups and Invariant Subspaces. Let's map out the hidden, stable rooms within the operator's architecture.
Finding invariant subspaces directly in an infinite dimensional space is notoriously tough. Honestly, it's like trying to find a stable room inside a constantly shifting maze. So the authors cleverly introduce a continuous semigroup of weighted composition operators to act as a backdoor. They prove this beautiful mathematical equivalence. If a subspace is stable under this entire continuous family of operators, it's going to be perfectly stable under our single Cesaro operator. This table perfectly maps out the logical chain they use to build a complete characterization. They take our continuous semigroup and linearize it into a translation semigroup. Once it's safely translated into that specific space, it unlocks the ability to use the famous Bjorling-Lax theorem. In operator theory, Bjorling-Lax is basically the master key for characterizing exactly what these shift-invariant subspaces look like. It allows us to catalog them completely.
So, grounding all this abstract math in reality for a second, what do these stable rooms actually look like? Well, one major type of these invariant subspaces simply consists of functions that flatline to 0 across a specific starting interval, up to a point A, before they start behaving normally. It's essentially a pocket of nothingness that the operator strictly respects and preserves. It never lets the function bleed back into that zeroed-out territory.
We've seen just how elegant and strict the anatomy of the real variable Cesaro operator is on the L2 space. But as we wrap up this explainer, the authors leave us with a hint about a subsequent paper that expands this exact analysis to LP spaces. And that leaves us with a really provocative thought. When we break away from the comfortable symmetry of L2, is this beautiful normality going to hold up? Or are these invariant subspaces about to become exponentially wilder? That is definitely something we're going to have to keep an eye out for.